Today we will start the constrained and unconstrained optimization. In the first lecture, we will discuss little bit about the preliminaries of optimization. If you see what is optimization, optimization usually we tell as a mathematical process. Optimization is a mathematical discipline that concerns with the minimum, finding the minimum or maximum value of an objective function, where the objective function consisting of one or more than one variables subject to certain constraints or restrictions we say. So, basically the optimization means we have a function of several variables and certain constraints are there. We want to optimize it, that is we want to minimize or maximize the function. Basically this optimization technique or operations research initiated in 1940s during Second World War. So, let us see one particular problem. If you see this particular problem, we have a machines, three machines we are having M1, M2 and M3. These machines can produce 4 products P1, P2, P3 and P4. Each machine can produce how much quantity of each product is written. On this column, if you see the last column, total time available per week, say in terms of minutes, 3000 minutes, 9500 minutes, 6300 minutes, and the per unit profit is also given on the last row. So, if I want to develop an optimization problem from this, where I have some machines are producing some products, what is the production rate that is given to us, what is the time available that is given to us, and what is the unit profit that also is given to us. So, from here if I want to optimize this particular problem, I can assume that x j is the number of units that the product j produces. X j is the number of units that the product j is being producing per week say. So, our point will be we can develop a function z equals, what will be the this one, our aim is I am producing x1 quantity of product P1, x2 quantity of product P2 like this, and per unit profit is this one. So, therefore, 7.5 is the unit profit per product x1. So, 7.5 into x1 plus 4.6 into x2 plus 9.2 into x3 plus 5.2 into x4. So, this is the actual profit if I am producing x1 quantity of product P1, x2 quantity of product P2, x3 quantity of product P3 like this, and their unit profit is this. I can find out one objective function like this. So, this is a function z which is a function of 4 variables, but this is only not the thing. There are certain constraints, because each machine can produce a maximum quantity of each product and the time constraint is also given. That means, if you see this first row for the machine M1, it can produce maximum of 2.7 of product P1, that is 2.7 x1 it can produce, plus for product P2 it is 3. So, it is 3 x2 plus 4.6 into x3, here it is 4.6, and for the product 4 it is 3. So, it is 3 x4. So, this is the, this machine can produce these 4 products within this time, but we have the available time limit is 3000. That means, I have to produce this total product, this one within this time. So, it should be less than equals 3000. That means, total time cannot exceed the 3000 units of time. Similarly, I can create another one for the second row, that is for machine M2, that is 2 x1 plus 7 x2 plus 2 x3 plus 5.1 into x4, which should be less than equals 9500. So, this is the second one, and for the third machine it is 2.4 into x 1 plus 4 x 2 plus 6.1 into x 3 plus 3 x 4, which is less than equals 6300. So, if you see, this is the objective function and these are the constraints or the restrictions, where obviously I will tell that x j is greater than equals 0, where j is 1, 2, 3 and 4. Since these are the products, so they cannot be negative. So, like this way I have formulated for this particular table one optimization problem. If you see here, this is the objective function and this is the constraints. So, optimization is a technique by which we can find out the values of the decision variables, say here x 1, x 2, x 3 and x 4, which will satisfy these constraints. And since it is a objective function and this is a profit function, so obviously we will try to maximize this function. Always we will try to maximize. So, maximize z equals this subject to this one. So, this is the basic idea of the optimization. Now, your optimization, if you see, various type of optimizations are there. One I can tell as constrained optimization, another one we can tell as unconstrained optimization. The meaning of constrained and unconstrained optimization means, unconstrained means only you have the objective function and you want to find out the optimum value of this objective function without using these constraints. So, this is if these particular constraints are not there, if I have only say max z equals x 1 plus x 2. So, this is one unconstrained optimization problem, whereas if I have the constraints, then we can tell that this is a constrained optimization. So, this second one is the constrained optimization, whatever we have discussed. So, this is one part. The other part is, I can put it as, it can be linear, it can be non-linear also. Linear means whatever objective functions you are considering here, the objective function should be linear in nature. So, as you know, one particular function may be linear function. Linear function means here just like x 1, x 2, x 3, x 4 is there. So, this is linear and the constraints are also linear. And other type of function I can make, that is say maximize z, which is equal say x square plus y square. So, it becomes non-linear. So, in optimization we try to solve both linear and non-linear functions in both cases. It may be linear, it may be non-linear. The other type which we can talk about, that is about the variables, that is it should be discrete, it can be continuous or it can be probabilistic. So, whenever you are talking about the decision variables, that is for this particular problem x 1, x 2, x 3, x 4 are decision variables, what type of variables are they? So, they may be discrete values they can take continuous values, that is any value on the real line, or the values may be probabilistic. If it is probabilistic, then we have to convert it into the corresponding continuous cases. So, the optimization I can derive like this, it can be unconstrained or constrained optimization. The problem may be linear, it can be non-linear. The decision variables which we are associating, they may be discrete, they may be continuous or they may be probabilistic. Now, let us go little bit about little mathematics, which is required for the solution of the initial problem, because after this we will start the linear programming problem at first. So, before going through the linear programming problem, let us see some basic definitions which you may be knowing. So, we will just brush up all these things. One is vector space. Whenever you are writing a matrix, you sometimes you write a matrix like this 1, 2, 3, 4, 5, or sometimes you write a matrix that is 1, 2 also. So, the first one is a row vector, we call it, the second one is a column vector. So, the vectors can be given, you know, may be knowing this is a row vector, then it is a column vector, and this row vector or vector can be given geometric representations also. If you think this A1, A2, this is a vector. So, this represents a point in two dimensional space. Please note this one. This represents a point in two dimensional space. Similarly, if I take a point, if I take a vector like this A1, A2, A3, this will represent a point in three dimensional space. And if I take a vector of n elements A1, A2, An, then also if I imagine it, then it will be one point in n dimensional vectors. And you have to remember that the row vector and the column vector both are equivalent. Next one is null vector. Null vector is denoted by this O, where all the elements are 0 of that vector, that is it will look like this. So, this is a null vector. Similarly, you are having the unit vector. Unit vector we define like this. I can tell E1 equals this thing, E2 will be equals to 0, 1 and all other elements are 0. Similarly, En will be like this. So, basically the unit vector you can denote by Ei, where the vector with unity as a value of the ith component, or in other sense for Ei the value of the ith component will be 1 and the value of the other elements will be 0, which we have represented like this. I think it is clear that unit vector is the vector whose ith component is 1 and all other elements are zeros. Now, suppose you have a set of vectors x1, x2, xn. So, you have set of n vectors which is say closed, which is closed under addition and multiplication, which is closed under addition and these two factors multiplication. Then we call that this set of n vectors will form a vector space. So, basically what is a vector space? If I have a set of n vectors x1, x2, xn, which is closed under addition and multiplication, then this set of n vectors will form a vector space. So, quite naturally the question will come, what do you mean by closed under addition? Closed under addition means if we take the sum of any two vectors, then the resultant vector will also be a member of the set. So, if x1, x2, xn is there, if I take addition of any of these two, then the resultant or the sum of any two vectors will also be a member of the set. Then we say that it is closed under addition. On the same way, multiplication, closed under multiplication means whenever I have two vectors, if I take any two vectors from set of n vectors x1, x2, xn and if I multiply, then resultant vector should also be a member of this x1, x2, xn. So, basically closed under addition and multiplication means whenever you will perform these two arithmetic operations, the resultant vector also belongs to the set itself. As an example, if you see set of all real numbers or set of all complex numbers, if you take, they will form a vector space. So, set of all real numbers, we are saying set of all real numbers, similarly say set of all complex numbers, set of all complex numbers, they will form vector space. Suppose I take a polynomial, set of polynomials of degree n, what happens? Set of polynomials of degree n, will it form a vector space or not? If I think I can take any two polynomials like this of degree n, x n plus a 1 x n minus 1 like this way plus a n. I am taking another one q n minus x n plus b 1 x n minus 1 like this b n. If I form the p n plus q n, and if you see p n plus q n, this x n vanishes. Therefore, the sum p n plus q n is a polynomial, that is true, it is a polynomial of degree, how much? The degree will be not n, because the nth term to the power nth term vanishes. So, the degree is n minus 1. So, from here we can conclude that means addition, after addition whatever result you are getting, that does not belongs to the set of polynomials of degree n. So, in other sense you can say that the set of polynomials of degree n will not form a vector space. So, I hope it is clear. Let us go to the next one, that is linear combination, which is very important, these parts which we will be using afterwards. You have a vector A, I am just writing in simple form, belongs to R n, say this will be a linear combination of the vectors a 1, a 2, a n, if we can form like this, a equals lambda 1 a 1 plus lambda 2 a 2 like this way plus lambda n a n for some scalars lambda I, for some scalars lambda I. So, if I represent A in terms of some n vectors a 1, a 2, a n like this way, A equals lambda 1 a 1 plus lambda 2 a 2 plus lambda n a n, where lambda i's are scalars. So, then we say A is a linear combination of a 1, a 2, a n. In addition to this, if summation over I equals 1 to n, lambda I, this is equals to 1. That means, summation of these all scalars is equals to 1. Then this linear combination we call it as convex combination. We call it as convex combination. So, if I can represent a vector A like this in terms of n vectors a 1, a 2, a n like this, A equals lambda 1 a 1 lambda plus lambda 2 a 2 plus lambda n a n, and if summation I equals 1 to n lambda I equals 1, then the combination we call it as convex combination. If you consider three vectors a 1 equals this, if you have the other vector a 2 equals minus 1, 1 and minus 1 say, and if I take another one say 0, 3, 2. Can I write down A3 equals how much? A3 is A1 1 into A1 plus 1 into I2. So, 1 minus 1 0, 2 plus 1 3 and 3 minus 1 2. So, basically I have 3 vectors A1, A2, A3. I am writing A3 as a linear combination of A1 and A2, where lambda 1 is 1 and lambda 2 is 1. So, this is a combination, linear combination of these two. From this linear combination itself, we come to the other one, that is linear dependence. You may have studied it in matrix notations. Linear dependence. So, you have a set of n vectors A1, A2, An. You have the set of n vectors A1, A2, An, and I will say that this set of n vectors are linearly dependent if there exists some lambda I, not all 0. Some lambda i's I can find out where all the lambda i's will not be vanishing, and this lambda 1 A1 plus lambda 2 A2 like this way plus lambda n An, which is equals to 0. Then we say that A1, A2, An, these n vectors are linearly dependent. So, please note that here all the lambda i's will not be 0. In the earlier example, if you take this example, I think 1 into A1 plus 1 into A2 minus 1 into A3, this is equals 0. 1 into A1 plus A2, this is 0. 2 plus 1 3 minus 3 0. Similarly, 3 minus 1 2 minus 2. So, this is 0. Therefore, we can say that these vectors A1, A2, A3, these vectors are linearly dependent. On the other hand, if you see, if I can find out the vectors such that if lambda 1 A1 plus, let me write it in the next page, that would be better. If you have n vectors A1, A2, An, and like linear dependency, I am getting lambda 2 A2 plus lambda n An, this is equals 0. Say this holds, this one holds if all the lambda is vanishes, that is lambda 1 equals lambda 2 equals lambda n equals 0. Then we say that these vectors A1, A2, An are linearly independent. This we will use frequently. So, please note the definition of linearly independent set of vectors. A1, A2, An will be linearly independent if for some scalars lambda is, we can get one equation like this, lambda 1 A1 plus lambda 2 A2 plus lambda n An equals 0, this holds. If all these scalars vanishes, then only we say that these vectors are linearly independent. For example, if I take A1 equals 1 2, say A2 equals minus 1 1, and if I take lambda 1 into 1 2 plus into plus lambda 2 into minus 1 and 1. Can you find out some value of lambda 1, non-zero values of lambda 1 and lambda 2 for which this will vanish? But if we calculate, you will find I am not getting any value. If I solve, this will hold if your lambda 1 is 0 and lambda 2 is 0 only. So, we say that this lambda 1 equals 0 and lambda 2 equals 0. So, this A1 and A2 are linearly independent. So, basically if three vectors are two vectors are linearly dependent, geometrically means they lie on the same line, and whenever some vectors are linearly independent, that means one vector can be represented as linear combination of the others. So, that is one thing. Next is spanning set. You have the set of all vectors in Rn. From here, if I can get a set of vectors A1, A2, AR, say, we say that this set of R vectors A1, A2, AR will span or generate Rn. Means, if I take any linear combination of this, that will be a vector of Rn, or in other sense, other way I can tell that from Rn, if you take any vector, that will be a linear combination of this A1, A2, AR. So, therefore, if in Rn I can find out a set of vectors A1, A2, AR, which can generate or span all the vectors of this Rn, then we say this set as a spanning set. This, consider this one E1, E2, En. This set spans Rn, I think, means using this set, linear combination of this set will be giving us any vector of Rn, because I can write down something like this: A equals A1 E1 plus A2 E2 plus AN En. For certain values of A1, A2, AN, I can obtain this value. So, this E1, E2, En spans all the vectors of Rn. Similarly, there is another concept which we call as basic, not basis, but it is basis. So, a basis for this Rn is a linearly independent subset of vectors where which spans the entire space. So, basically basis is nothing but the linearly independent, please note this one, linearly independent set of vectors. These are linearly independent set of n vectors A1, A2, An, which spans the entire vector space, and this we call as the basis. And similarly, your dimension is the number of linearly independent vectors in the spanning set is known as the dimension of the basis. So, in one word, basis is nothing but a set of linearly independent n vectors which spans the entire Rn, and the dimension is the elements with number of elements or number of linearly independent columns of that set. So, next we will start in the next class.